Fine, Chaitra. So now basically today in this session we'll continue with MOSFET amplifiers and we'll try to see through simulation some of the properties of the amplifiers. So typically speaking, in this session we will try to understand the calculation of output resistance of amplifier. Now, what exactly we mean by this and how this is different from R out or R not, let us try to understand first. So, simply speaking, if I have a simple amplifier, like for example, if I connect a simple NMOS with input over here and I try to take the outcome over here with this being your VDD. So basically, if I try to understand the input and output resistance of any amplifier, if I just want to understand through a black box, see if I have an amplifier here and my input, let's say, is being applied something like this. Let's say I'm applying V signal, and let's say I'm taking the output resistance across a load resistance RL, and I'll say this as the signal resistance. So if I try to look from the output side and want to calculate the resistance, so all the resistance that are seen from the output side, they are specifically termed as the output resistance. And similarly, if I just look from the input side where my input signal is being applied, and if I see through the amplifier, this will be my amplifier. So this is basically an amplifier. If I see through the amplifier, whatever resistance I'm able to see, those resistance are basically your input resistance. Now to make it a little bit clear, I need to remove this black box and need to put a proper amplifier. Then possibly whatever resistance I'm able to see, there could be some resistance connected in series with R6, parallel with R6. I need to solve that. So the combination of overall resistance, whatever I am going to achieve, that I'm going to call it as an input resistance. Similarly, I need to solve all the resistance over here, whatever I can see over here, including the resistance that fall at the output side of the amplifier. When I try to solve them and the final outcome resistance, whatever I'm going to get, that is basically my output resistance. So that's what is we are going to calculate here, R out. Now, why R in and R out are very important, and how that R in and R out is different from R naught. See, basically R naught is what, it's a small and finite. It is also an output resistance because we see that resistance during the outcome of the current flow. That means we see that particular small r naught when we operate on the MOSFET. So small r naught will also be part of your R out along with other resistance. So this is an intrinsic resistance, that is by default R out will be small finite output resistance by default. If if no load resistance is being attached over here, then what would be my output resistance? It will be equal to R out. If some load resistance is being attached over here and along with that there are any other resistance, then that particular those resistance will also be taken into consideration, and finally whatever is my resistance IMC, that will be my final resistance. So based on that, now let us try to identify how exactly we can see. Now we know that the MOSFET simply we cannot analyze in its form. So we'll convert this into a small signal model so that looking from the input side and looking from the output side, we can easily do it. So like that, let us try to build a proper amplifier where I have an RD and I'll also take a load resistance. Load resistance is something where this is the combination of resistance that is clubbed together over here, which can be from the next stage input. I'll tell you what exactly I mean by that. So let's say I have this particular. Again, I am assuming here that a DC signal is being used for biasing. That's why I'm not showing that DC signal over here. Like yesterday, I showed you particularly here. It is understood that we have already biased it in the saturation. It is understood because now we are dealing with MOSFET as an amplifier. So that means by default, my MOSFET has to be in the saturation region. Okay. So RL, the concept of RL is something like this. If I have a block 1 and that is connected to one more block. See, always in the industry, it is not that you always use a standalone amplifier, right? It comes with multiple structured format. Basically, in the sense, all those amplifiers are all the different blocks are interconnected together. And let's say if I have a blocks, multiple blocks, maybe amplifier, oscillator, or some other block like PLL or any other blocks, they are connected in this manner, in an haphazardous manner. And I want to calculate the input and output resistance of each block. Then input will be towards the input of those particular block and output will be towards the output of those particular block. But when doing that particular thing, if you see, if I come over here and if I see at this particular point, let's say at point A, what is the load for this particular block 1? The load for this block 1 is the resistance offered by the block 2 at its input is acting as a load. That is basically the representation of the load resistance. Now, I do not know practically what would come in front of this block. There could be multiple blocks, there could be a simple block, there could be one or two blocks, there could be capacitive block, there could be inductive block. I do not know what is going to come. So to club and to represent on behalf of them what is going to come in front of these blocks, I just say that there is some block and that block also will have some sort of input resistance, and that input resistance itself is acting as a load resistance because both are interconnected this way. And that's why I try to represent any time for any given circuit with a simple resistance RL. And what is usually the value of RL? RL will be very large. Why it is very large? Because you don't know what is the next state values and what would be the next stages that are connected over here, and those all stages put together would offer some sort of resistance, and those resistance will be very large. And also there is one few more other reasons why the load resistance has to be large. We'll try to discuss about that sometime later, but this is basically the general concept of load resistance. Fine. So let us try to remove these things. Now, once I have this particular block or the amplifier, simple amplifier circuit, we yesterday have drawn the small signal equivalent. So basically, how do I draw? I try to represent. So this is my source, gate, drain. So I have my source here. I try to represent my MOSFET with the dependent current source having a value of Gm times VGS. And then I try to represent here my drain, and sorry, this is my gate, right? And this will be my source. So this is simply a MOSFET model, but here with respect to this circuit, I have some sort of resistors also being included. And out of that, the most important resistance is, first of all, I need to include the finite output resistance, small r naught, that comes between drain and source, because that will be between the drain and source within the channel. The next is I have RD and I have RL. Now always remember, whenever you convert this particular given circuit in its small signal model, the very first rule is that you are supposed to short all the DC supplies. So basically, if there is a DC supply, those will be connected to ground. So that's how the analysis part goes. So here is my DC supply. So if this gets connected to ground, this circuit would look like something like this. This portion would be looking something like this. So this side it will be input. I can say this will be RD, and to the same node RL is connected, and that is also connected towards the ground. And anyhow, my R naught will be between this particular. Here will be my R naught, and the source is also grounded. So basically, if you try to observe R naught, RD, and RL put together, they all are parallelly connected. So that means I have to represent three resistance. If RD and RL are not specified, then only R0 will be acting as single resistance at the output side. And if I try to calculate the output resistance, only R0 will be acting as my output resistance. Now, because RD and RL are also connected together, they are basically your three resistances that will be placed in common. So if I just try to figure out what is R out, that will be parallel combination of R naught parallel RL parallel RD. And R naught we will calculate through the simulation. RD and RL are the known values that will be given. So if I do the parallel combination of all those things, I'll be getting R naught. So R out. So that is my output resistance. So this is basically how do we calculate the output resistance. Now the same thing, let us try to figure out through simulation how exactly it is going to look. Now, before we actually get into this R out things, so this is basically a simple case one, a simple amplifier configuration. Now, we'll just look into another case also. We have something called as diode connected load amplifier. That means if I have a particular MOSFET which is connected in this manner where your gate and drain are shorted, and if you try to see the output over here, this particular kind of MOSFET where gate and drain are connected together, they're shorted together, they are being specifically called as diode connected load. Why it is diode connected load? Because if you short gate and drain this way, it is going to act like a simple kind of, it behaves like a diode, or it looks like a diode. And also when you see any, when you say that any particular configuration is behaving as an amplifier, and you need to satisfy the condition VDS should be greater than or equal to VGS minus VT. This condition has to be satisfied. Now how this condition would be satisfied over here, let's see. See, if I consider, let VD equal to 3 volt, VT equal to 1 volt. Now let us try to use this condition. If VD is 3 volt, I'll put this here. And since D and G are shorted, that means VG will also be equal to 3 volts and threshold is 1 volt. So this condition is always being satisfied. And that's how this is a particular, a best example of an amplifier which will be biased always in the saturation. Now here, this is something called as self-biasing, where no need to have an external biasing things or external biasing supply. This is automatically biased the moment you connect gate and drain together. So that means this MOSFET will be always in saturation. So all these two combination of MOSFET amplifiers, whatever you are seeing here, if you observe, if you just even see here, the when you want to take the output is taken between drain and source. Basically, output is between. See, here is my output between one end is connected towards the V out and another is towards the ground, and the ground is also being connected with the source. That means I can say output is between drain and source, right? So, and I have my input between gate and source. Here source is common, and that's why this particular configuration is also called by the name common source. common source amplifier. So I'm just giving a gist of how we can identify any particular amplifier based on the given circuit. Now, even this particular configuration, in fact, this is another subset of the above amplifier configuration. Here also, if you see, input is between gate and source, output is between drain and source happens to be common. It is also a subset of common source amplifier. And sometimes it is also called by the name grounded source because source is grounded. So whatever we are looking over here, these are the combination of your common source amplifiers. We'll talk about other configurations which are common drain and common gate sometime later, but the most specific and most common amplifier configurations that we use usually in all our analysis will be our common source amplifier. Now, so just like the way how we calculated R out for the case one common source amplifier, a simplified and a general common source amplifier, let's try to calculate what would be the output resistance of this particular configuration. Will that change or how exactly it looks? And then based on that, can try to summarize the output resistance, what should be the value and how exactly which configuration is best suited, why these many configurations are there, and which configuration should be used, which is the most preferred configurations. All these answers we'll try to figure out sometimes later down the line when we try to understand these different parameters. Now, so when we have this particular thing, now let us try to represent this particular MOSFET amplifier through its small signal representation. So we have gate, then we have ID as GM times VGS. That's your source. Then we have drain. So I have not taken here RD and RL. If we take that, RD and RL would come in parallel with R naught. So that particular thing you can remember. Now, along with that, this is the representation of simple MOSFET. But here in this thing, we can see gate and drain are shorted. That means, let me just rub this. Just make sure that I'll write it here. Yeah. So here, if you see, gate and drain are shorted this way. That means the drain current that was flowing over here, ID, comes over here like this also. So here you see gate, and because gate and drain are shorted, so in my small signal model also I did the same thing. So basically I have this particular thing. So now let us try to figure out. Now in my previous case it was very simple because I just looked at the output side and I saw that there are three combination of resistances which are in parallel. That's why I said output resistance is a parallel combination of all the three resistances. But now if I just look from the output side over here, now because at the output side there is a one particular wire that goes towards the input, so it is not as straightforward. I cannot claim that it would be a simply R naught. I need to solve this particular thing. So let us try to solve this particular thing and figure out how exactly it is going to look. Now let us try to figure out how exactly it is going to look. So for that, let me write the equation. ID is equal to, see, there is this ID which is marked in red color. So that ID which starts from my drain breaks into two paths, one here and another through R naught. So that means by that notion, I can write a simple KVL as G. And what is, how do I represent this ID over here? How do I represent ID in terms of my resistance? So here I can say this ID, can I write, because the ID is coming from my VDS, so can I write VDS upon R naught? That's my ID over here. So I can write this will be current entering the node which is my this ID is equal to current leaving the node. Gm times VGS plus VDS upon R naught. Now, because G and D are shorted, that means VGS is equal to VDS. So therefore, my ID would now look like Gm times VDS plus VDS upon R naught. Further, let us try to simplify this. I'll take out VDS out, Gm plus 1 by R naught. So let us try to further simplify this. I want to calculate the output resistance. So whatever the resistance I am going to get, that should be represented in terms of its output parameters, which are nothing but your drain current and the drain to source voltage. So I'll bring this VDS down over here. What is that I want to get? Gm plus 1 by R naught. So basically this thing R out, I can say that Gm plus 1 by R naught would be your R out. Or specifically, if I want to further simplify to make it look like the way how we have written for the previous configuration where we wrote in terms of parallel combination. So let us try to restructure this expression. Let us try to restructure this expression to some extent, something like this. Let us say I'll try to so in fact, BDS by ID is your R naught, right? So here I cannot write RDS. So let's write ID by VDS only for time being. Yeah. So now VDS by ID would be 1 over Gm plus 1 by R naught. So if I solve it further, this would be Gm R naught plus 1 divided by R naught. Upon further solving, R naught divided by Gm R naught plus 1. So let's further solve this. VDS by ID, dividing both numerator and denominator by R naught. So I'll just write divide numerator and denominator by R naught. Why I am doing? Just for mathematical calculation. So if I do that R naught by R naught, then this will be Gm R naught plus 1 by R naught. So if I do this, it will be 1 over, sorry, let's not divide by R naught, let's divide by Gm. Sorry about that. Let's divide by Gm. Just want to make it look like the expression what we saw in the previous thing. Basically in terms of parallel combination. R naught by Gm divided by this here will be 1 by Gm plus R naught. So this you can write something like this: R naught into 1 by Gm divided by R naught plus 1 by Gm. Can I write like this? So now if you closely observe, this is basically your R out and your final expression is this, which is R naught into 1 by Gm divided by R naught plus 1 by Gm. Can I write this as R naught parallel 1 by Gm? Because what is the parallel resistance equation? If I have R1 parallel R2, R1 R2 divided by R1 plus R2, is it not looking that way? R1 R2 divided by R1 plus R2. So that's why I can say that finally my output resistance for a diode connected load R out would be equal to R naught parallel 1 by Gm. Now this way it will be easy for to remember Rather than you can remember this also, it is basically Gm plus 1 by R naught, but it will be easy for us to remember the output resistance of my diode connected load. Now, along with that, now look here. Here I just took R naught. If in the place of R naught, along with R naught, if there would have been RL and RD, then that would come in parallel with R naught. So possibly that would make us this entire thing R naught parallel RD parallel R L parallel 1 by GM. So there will be four resistances. Now here I have not taken that, but practically if those scenario comes, you can take that also. So this is basically how your R out would come into picture. So this is basically to how do we calculate the output resistance. Now let's quickly try to look into the simulation scenarios. Get installed.
Yes, sir.
Yeah. So what I was telling is, so I have taken the same NMOS characterization circuit where I have this NMOS, and I have here taken multiple sources. I'm just taking the VGS source, and I'm also taking the VBS because I want to vary the body voltage also, and to see how the impact of output resistance would come later in the other configuration. So for that purpose, I have taken. Otherwise, you can connect this to the source also, or maybe I'll just do it here. When we come to that particular thing, we'll take a look at that. So we can just connect this way. And then I have taken the AC source over here with DC magnitude, DC voltage of 900 millivolt and AC magnitude of 1 volt. Now the reason for this, let's try to understand why we are choosing this one when we try to do the simulation. So I have launched the ADL through this launch ADL window. When I launch that ADL window, this dialog box will come. So I'll do the copy from cell view and I'll put VBS as 0. Anyhow, I think I'm right now will not require these things because I have connected VBS. Let's delete it once again, will do. Yeah, VGS, I'll take it as 900 milli. And then we'll because I am calculating the output resistance right now, I'm just trying to observe what is the scenario at the output side. So here I'll just choose the AC response, AC analysis. I have taken the frequency sweep from 1 to 100 megahertz. I'll say okay. And then outputs to be plotted. I need to plot ID versus VDS only, but with respect to frequency. So because I'm doing the frequency analysis, look how exactly this differs if I replace this AC source with a DC source. Let's try to do that bifurcation. So I'll run it. So this is basically the frequency response of ID versus VDS with respect to your this particular circuit. Now the same graph, if we try to do the DC analysis, and if we try to see what is the difference DC analysis with AC analysis is what here when we try to do the DC analysis, it is purely with respect to the DC supplies, and then we vary the voltage from 10 to 1.8. With respect to the DC analysis, you're going to get the pure characterization. So I'll disable the AC analysis over here and I'll run it. That's the difference. This your graph which you did the DC analysis, here we get the graph of ID versus VDS. Now because here also, from here also we can do the same analysis what I'm going to do it from the AC analysis, but here the look at the difference. Here your current varies across various frequencies, and that's how the graph looks like this graph and this graph. This is purely ID versus VDS characterization. Now what exactly we do when we want to calculate the small r out, because see in our this scenario we have already told that what is the output resistance. If RD and RL is not there, r out is nothing but your small r naught, and whatever we have done the exercise to calculate the small r naught, we can replicate the same scenario. So let us try to replicate the same scenario, and we have calculated this id versus vds. So if I have id versus vds, now I require vd by id, so I can just take the reciprocal of this. So I can just take the reciprocal, I'll send it to the calculator, I'll use the function, I'll take this 1 by x, and I'll say this. So whatever the resistance I can see at exactly what? Let's try to mark it to 900. So there you go. So that's 14.844. See, you can see in the bracket there is a K written over here. Let's mark it. Yeah, if you just see here, 14 exactly. Let's mark it at exactly 900. 14.844 K 1 by A. What exactly this 1 by A indicates? That indicates A is, see, 1 indicates is basically that is your the magnitude of your voltage that you took over here. If you see over here in the schematic, what is the magnitude of this supply? AC magnitude you took 1, right? So that is your 1 volt, and 1 volt, that is V divided by A. That means V by A will be your R and the unit will be your ohm. So that's how to represent this particular thing. We can take that AC source over there. So that means 14.844 kilo ohm. So this is basically what we are going to see over here. So this is how we can calculate the output resistance with respect to the DC analysis over here. And the same can be done with respect to AC analysis. So this particular thing over here, the same thing can be done over here. Okay. So now let us try to send this particular graph, because we have done the we have drafted the AC analysis graph. So let us try to send this to calculator. Now here also this is the graph of ID versus VDS, and I want the reciprocal of that. I'll try to take the reciprocal of this, and now I'll try to flip it once again. Let's try to redo it once again. So let us send it to calculator. Once again, it's not taking. Let's try to replot it. So this anyhow, let's try to plot it one more time. Oh, AC analysis is disabled, right? Yeah, I'll run it one more time. Yeah, now let's try to if I take the 1 over x. Yeah, now if you see, if I mark, now if you see, across all the frequency from 1 to 1 kilohertz or 100 megahertz, if you see, so this is basically your, try to change the color. The yellow one is your basically the resistance. Okay, now across all the frequency range, now your resistance is getting calculated as 42.6 kilo ohm. But the same resistance, when you calculated with the DC analysis, it was coming out to be 14.844 kilo ohm. Now which one is correct, or which methodology is correct, which one to consider? Now here what we did the um, we plotted ID versus VDS graph, and we took the reciprocal of that, and whatever the value we get over here, that's basically my finite output resistance, and the same is nothing but my output resistance over here. And the same thing when we did with respect to AC response, we took the AC graph and we reversed that graph. Now we are here, we are getting the graph as 42.6 kilo ohms. Even again, see, if you see, it is 1 by A, 42.608965753 K. In the bracket, it is written as 1 by A. That means it is 1 represents the AC magnitude. It is in terms of volt. Volt by ampere will be your resistance. So that's kilo ohm. So now, should we take this as, should we consider this as my output resistance, or should we consider the DC as my output resistance? Now, look here. We cannot claim this as the output resistance, because how we calculate the output resistance? When we calculated the output resistance, remember here what we did? We shorted all our DC sources. When we short all our DC sources, see, the notion of calculation of output resistance is what? We short the DC sources and we apply some AC supply over here. That's how we calculate. When we short these DC sources, we'll apply some AC source at the output side, and from there, because see, how do we calculate the resistance? We require some supply. We require, see, I is V is equal to IR, and to calculate R, I require what? V by I. And where this V comes from? This V we have to apply, because now when we do the small signal analysis, when we try to model this, all my DC supplies will be grounded. See, the same scenario was not true when we calculated the small output resistance or not, because at that time DC sources were there. Actually, we haven't applied any AC source. But right now, since we are applying some AC source over here, and then we calculate the output resistance, so doing the calculating the R output through the DC analysis is a wrong thing, and we have to calculate the output resistance through the AC analysis only. And that is the reason why I apply the AC supply. And in that AC supply, you mentioned what is the DC magnitude, because that is what the basically the voltage is. So that is basically how exactly we try to push the input, push some voltage over here. So through this voltage, whatever is the current that is generating over here, that current will fetch me the output resistance, and that's what we have seen over here. So this is basically the finite, I mean, the R out, including all your R naught and RL, if anything is there. If nothing is there, then that would be your final output. So this is basically how across all the frequency you can see the output resistance that is being displayed over here. So that's how we calculate the output resistance. So this is basically how do we calculate the output resistance. So similarly, there are certain things. How do we measure the input resistance, and why do we require input resistance and output resistance for an amplifier? We'll talk about that in the next session. Basically, those are required to ensure proper functioning of any particular amplifier. If it is an voltage amplifier, how exactly it should perform, and if it is a current amplifier, how exactly it should perform, we should know that. So for to understand all those things, these parameters are really very important. So that is the reason why we go ahead with the calculation of output resistance and input resistance. So that's it from my end today. So